Okay, so the next thing we'll figure out is the coordinates of a wrap of pi over 3. And the way this derivation is going to go, just to save a little time, a few facts that we know. What we're going to do is we're going to take this upper semicircle, which would be an arc of length pi, and divide it into thirds. So you can see these three little pieces I've created here and the three segments that go along with them. So you notice that a wrap of pi over 3 and a wrap of 2 pi over 3, so a third of the way to pi and 2/3 of the way to pi, they're symmetric to the y-axis. So if I give pi over 3 coordinates AB, then 2 pi over 3 would have to have very similar coordinates, just with a negative A and a B. Well, that means that the segment joining negative AB and positive AB, this little segment right here, this has to have a distance equal to 2a, and for right now I'm just going to call that d1. Likewise, the segment joining AB and 1, 0 will also have to have a distance of 2a, and I'll call that one for right now d2. So those distances have to be equal, and the rest of the derivations is going to fall in line from the distance formula. So d1 equals d2 is where it'll start. d1 I know to be 2a. You can just see that because we're moving horizontally from negative a to positive a. d2, meanwhile, will have a distance that I can describe with the distance formula. So it'll be the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates squared. So that would look like this. A minus 1 squared plus b minus 0 squared. All right, and then what I'm going to do first is I'm going to get rid of that nasty square root. Square the left side and you get 4a squared. Square the right side and you'll get rid of the square root. You'll get a minus 1 squared, and I'm going to just write that as b squared there instead of b minus 0 squared. In the next step, I'll expand a minus 1 squared. 4a squared equals a squared minus 2a plus 1 plus b squared. And then here's the step where it's very, very tempting to take that a squared and bring it over there and combine it with the 4a squared. But if you do that, you're going to screw it up and you're never going to figure out where you went wrong. The key is at this step is to pay attention to the fact that you've got an a squared plus a b squared on the right-hand side, and this is the unit circle, x squared plus y squared. Well, a is the x-coordinate and b is the y-coordinate, so a squared plus b squared has to be equal to 1. That's going to be true because we're on the unit circle. AB is a coordinate on the unit circle. So a squared plus b squared is 1, plus another 1 makes 2. So color back here. It would be 4a squared equals 2 minus 2a. And look at that, we got a quadratic to solve. I'm just going to bring it up here to finish it off. It would be 4a squared plus 2a minus 2. If we group everything on the same side, that would equal 0. Divide those even numbers out, it would be 2a squared plus a minus 1 equals 0. That looks like it has a chance to factor. Let's try it. 2a and a, and it's going to be 1 and negative 1. I think with the negative 1 here and the positive 1 here. Let's check that. Does it work? Does it work? Does it work? I think it does. That means either a equals 1/2 or a equals negative 1. Well, can a equal negative 1? No, a is in the first quadrant. So you silly quadratic gave me an extraneous solution. Throw that one out. That means a is equal to 1/2. So we got the x-coordinate of the circle wrap pi over 3. A equals 1/2. Well, what's the b? We have to go back to our circle. A squared plus b squared is equal to 1. A is 1/2. 1/2 squared plus b squared equals 1. Take my time here, it's getting kind of sloppy. Well, half squared is a quarter. And that means b squared is equal to 1 minus a quarter, which is 3/4. And that means the square root of 3/4 is equal to b, plus or minus, but we're in quadrant 1, so we'll take the positive. B would then equal root 3 over 2, because square root of 4 is 2. That means this ordered pair is 1/2 for the x-coordinate and root 3 over 2. So we figured out the coordinate of a wrap of pi over 3. 1/2 for the x, root 3 over 2 for the y. Basically, after we do that, all the other points fall in line. Because pi over 3 and then this point over here, pi over 6, are symmetric to the line y equals x, we can just argue that if pi over 3 has an ordered pair 1/2 root 3 over 2, then pi over 6 must have the inverse of that, root 3 over 2 comma 1/2. And you can try deriving it on your own using a very similar setup with congruent arcs here in quadrant 1 and quadrant 4 instead if you want. So once you have those 5 points, all of the rest of the points on the unit circle, as we saw with the pi over 4s, can be found just using the signs, the appropriate signs from the quadrant. Like quadrant 2 is negative x, positive y. Quadrant 3 is negative x, negative y. Quadrant 4 is positive x, negative y. And just match up the right wrap with the wrap from quadrant 1. So a wrap of 2 pi over 3, well, is right here. It's a lot like a wrap of pi over 3, but its x-coordinate is negative because it's in quadrant 2. So it's negative 1/2 comma root 3 over 2. And a wrap of 4 pi over 3, 4 pi over 3 is down here because it's pi over 3 larger than pi. Well, it's like the wrap of pi over 3, but its x and y are both negative. So negative 1/2, negative root 3 over 2. 5 pi over 3, same deal, but that one's in quadrant 4. Positive 1/2, negative root 3 over 2. And the same is true for all the pi over 6s that you need to know. 5 pi over 6 here in quadrant 3, just like pi over 6, but with a negative x-coordinate. 7 pi over 6 here in quadrant 3, negative x, negative y, and 11 pi over 6 here in quadrant 4 with a positive x and a negative y. So I think that's a wrap. Rotating wheel of death.